For visual relationship recognition, it is a task to recognize the relation between one subject and one object. For long-tail visual relationship recognition, it is to detect the relation, for those very infrequent relations. So those relations might, very rare in the real world, or maybe rare like for those subject and object. To take this as an example, in this image, so given an AI model, so we can recognize this subject of a dog and also the subject of a house. So for AI model, it is very difficult to recognize the dog is writing a house relation. It is very difficult because there's very few such examples in the training data. And so also like for this dog and a house, they are very common objects. So we can see there's some very long tail relationships. And also there's many like tail subjects and also tail objects. For example, the rhino and the gorilla. If we study the relation, of those long tail objects, and so it can be more complex and also more difficult to predict their relation. These are some other rare visual relationship examples. In the left one, it is a parrot riding a bicycle. In the right part is a monkey riding a dog. So given these two images, so the current AI model can recognize this is a parrot, this is a bicycle, a monkey, and dog. They are very common in the real world. But if you need to recognize their relationships, it can be very challenging because you have never seen, or maybe only seen maybe one or two such examples in the training data. So it's difficult to predict like for AI model. In order to study and also analyze this long-tail visual relationship recognition problem, so we have introduced these two benchmarks. The first one is VG8K LT benchmark. The second one is a GQA LT benchmark. For the VG8K LT, it contains 5,300 objects and 2,000 unique visual relations. It's built up from the visual genome dataset. For GQALT, it contains 1,700 different objects and 310 unique visual relationships. It's built up from GQA datasets. If you want to know more details about these two benchmarks, you can scan this QR code. So let's look at the data distribution for these two datasets. So we have illustrated the distribution for subjects and relationships and also objects. So from this figure, you can see how long tail it is. So let's take the relationship of the VGLK LT as one example. So for the top frequent relations, you can see it contains nearly like hundreds of thousands examples. But for the tail classes, it contains only very few number of examples, maybe 10 or 5. So when you predict the long tail classes with this data sets, it can be very challenging for current AI models. In order to better study and also analyze the long tail performance, so we break down the data into many, medium, and few. For many, we selected the top 5 most frequent classes. For medium, we selected the middle frequent 15 classes, and for tail, it's just the other 80% infrequent classes. And then we ask the AI model to predict the performance for each category. Regarding the evaluation metrics, we use the average per class accuracy to evaluate the model performance. We have 2 metrics. The first one is the relation O per class. It is the per class relationship classification performance and averaged across all relationship types. For subject object O per class, it is a per class subject and object classification performance averaged across all object types. In our challenge, we have provided all the open source code and data to the participants. So finally, there are overall 5 submissions in our leaderboard. We selected one winner. based on their performance on these two benchmarks. So here's the result. In this two benchmark, so there's one winner team, which is Gavin Wang. Their team has achieved the best performance on both benchmark. So he's the winner of our challenge. Yes, so congrats to the winner, and the winner is from the team from in Shanghai Technology University and also Shanghai Jiaotong University. The first author is Chen Yu Wang, second author is Shuo Wang, and the last author is Sheng Hua Gao. So today they cannot physically come to the CVPR, but they have pre-recorded the video to demonstrate their idea. And I think the first author is also like in the Zoom. So if you later on, if you have any questions, you can ask him.
Just
Hello everyone, I'm Chu. We're student at Shanghai University. Today, I'm pleased to bring out.
Sorry.
On the screen.
Yeah.
Sure.
It's a red there. And now again.
Yeah.
Yes.
So, using just program is actually using for visual relationship recognition. Yes, we will reveal the task of visual relationship recognition, which aims to predict the relationships between subjects and objects, while considering that there exists a long-term distribution. Compared to the single object recognition task, this task is different to its relational nature, especially when getting results of categories. Furthermore, the data set may use an recognition as illustrated in the image. The dog is riding on a horse. Previous works on long-term distribution recognition demonstrated that the final classification components of the model depends on two aspects: representation quality and classifier quality. The motivation behind our work is to improve the quality of both aspects in order to enhance the overall model performance. For improving the representation quality, we validate different methods on three aspects, which are global representation, local representation, and relational representation. For improving the classifier quality, we consider applying effective sampling strategy, decoupling classifier, and weighted loss function. This is the pattern of our approach. First, we input the images into a vision transformer network and use the MLA module to obtain visions for the subjects and objects. Then we construct a broad neural network that learns the representation of pairwise relationships given the subject-object pairs. Next, we incorporate the transformer module to define the relationship features. Finally, the refined shifted features are separately input into the corresponding classifiers to obtain the predicted categories. We will provide detailed explanations for each step afterwards. Compared to ResNet and which networks, vision transformers has more powerful feature representation ability. However, the VIT runs in a different way compared with other traditional networks. So if directly using ROI only or ROI alone, it is not suitable to extract the features. The recent work proposed a module for masking with overlap error, as shown in the diagram on the right. This module calculates the overlap region between the given region and region patch. The normalized values are then included into the intention map. This experimental results have demonstrated the effectiveness of this approach. After instructing features for subjects and objects, we adopted a special condition graph to the LTVRR relation feature implementation, as shown at the bottom. We applied a parent graph using parent features as node features. The initial features are based on the of the previous and update function. We also construct LTVRR special encodings as AG features. Through a message passing algorithm, we can ultimately characterize the connectivity of the graph. We found that directly constructing such a biparent graph would result in many more relation subject-object pairs. To alleviate the modulus bias towards that data, we proposed a negative samples reduction strategy, in which we first calculate the minimum errors IOU in the branches subject-object pairs and all possible gaps. Then ranking the IOU value to set out the first 50 samples. Then we employ the small module proposed into REST1. This module refines the features, machines, and it will step by considering the global context of the scene. Finally, the refined features are input into the corresponding classifiers to obtain class logics. Now let's move on to our experimental section. We conducted experiments on two data sets, which is a and a This data set will derived from the original data set with certain process that can be observed that which is a is relatively more complex. As for the evaluation metrics, we shape the accuracy of these states, many, medium, and few, based on the sample frequency, as well as the overall accuracy across both categories. We define our model with a long-tail function with the first entropy. Our method has demonstrated superior performance on which APK long-tail, especially for the future categories. We will observe significant performance improvements in both subject, object, and relation predictions, especially it achieves 23.4 forecast accuracy, outperforming the previous test by 4.4%. Regarding QA, our experimental results compared to the transformer, which is contrary to the theoretical expectations. In fact, due to the limitation in our current computational resources, we were unable to match the parameter settings of the original paper, including the network training levels. However, on the other hand, our experimental performance shows some improvements compared to another work RS We conducted extensive calculation studies on which APK 130% is the more challenging. For this, less than 50 is relatively 16 and obviously prove the relation on all settings. By using your transformer, plans can be further improved. Moreover, experimental loss in ability to demonstrate the effectiveness of negative samples reduction. The couple classifier and weighted loss function for the program classifier equation. In conclusion, in this work, we explored different methods for improving the recommendation and classifier, and the proposals that are important for the long-tail classification task. We also demonstrate the efficient transformer is a powerful platform and resistance. Also, the transformer is effective for this task. Last but not the least, we are further detected using clean text encoder for improving the classifier quality. Thank you for listening.
Do you have any questions? Okay.
If there's no any questions, let's thanks the authors again, and also thanks the presentation of the Chinese organizers.